Hello viewers, this is Dr. D. Rajalakshmi, Associate Professor in CSE Department of RMD Engineering College. Welcome to today's session on asymptotic notations. First, I would tell you the definitions of asymptotic notations like big O notation, big omega notation and theta notations. We would then see examples and properties of asymptotic notations. What's an asymptotic notation? What's the purpose of using it? Actually, analysis framework used for finding efficiency of an algorithm concentrates on the order of growth of an algorithm's basic operation count. So to compare and rank such orders of growth, we can use asymptotic notations. Let's see the informal definitions of big O notation, theta notation and omega notation. If at all, if f of n is in big O of g of n, then f of n is a class of functions that grow no faster than g of n. If f of n is said to be in theta of g of n, then f of n is a class of functions that grow in the same rate as that of g of n. If suppose f of n is said to be in omega of g of n, then f of n is a class of function that grow at least as fast as g of n. This is the diagrammatic representation of big O notation. Here, g of n grows faster than f of n or otherwise t of n. Here, t of n function and g of n functions are compared. T of n is said to be in big O of g of n, and this is the diagrammatic representation for the big O notation between t of n and g of n. So here g of n function, it grows faster than t of n. That is why t of n is in big O of g of n. Now this is the diagrammatic representation for big omega notation. Here if we see the graph, from the graph itself we can find out that t of n is growing faster than g of n function. So we can say that t of n is in big omega of g of n. Then the next one is the diagrammatic representation for big theta notation. Here both the functions are growing in the same order. So t of n is in theta of g of n. Now let's see the formal definition of asymptotic notations. If f of n is in big O of g of n, when it will be true means if the order of growth of f of n is less than or equal to order of growth of g of n. That is, if there exists a positive constant c and a non-negative integer n naught such that f of n is less than or equal to c into g of n for every n greater than or equal to n naught. The following are the examples for big O notation. We can say that 10n is in big O of n square. Why? Because order of growth of n is less than the order of growth of n square. This n function is growing slower than this n square. So we can say that n is in big O of n square. Similarly, then the next example is 5n plus 20 is in big O of n. When we see the asymptotic notations, or otherwise when we consider the order of growth, we need not consider the multiplicative constants. So we need not consider 5 and 20. Okay. So in the left hand side n is there and it is slow growing function than, or otherwise it is not slow growing function because on the right hand side also n is there. So both are having same order of growth. Both are growing in the same rate of speed only. So we can say that 5n plus 20 is in big O of n. Because the condition for big O notation is f of n must be less than or equal to some constant in g of n. Here both the functions are having same order of growth. We can say that 5n plus 20 is in big O of g of n. The next definition is for big omega notation. Here if the order of growth of f of n is greater than or equal to order of growth of g of n, then we can say that f of n is in omega of g of n. It means that if there exists positive constant c and a non-negative integer n naught such that f of n is greater than or equal to c into g of n for every n greater than or equal to n naught. If suppose the following are the examples. Here n cube is big omega of n square. What is the order of growth of left hand side function? N cube. What about the right hand side function? N square only. Left hand side function is fast growing function than the right hand side function. So we can say that f of n is, that is n cube is greater than or equal to n square. So n cube is in big omega of n square. Similarly here the left hand side function's order of growth is n square. Right hand side is also n square. Both the functions are having same order of growth. In that case also, because of this equal to condition, we can say that n into n minus 1 is in big omega of n square. Now let's see the properties of asymptotic notations. The very first property is f of n is in big O of f of n. It says that, it means that if any function is said to be an order of itself. For example, n is in order of big O of n, n square is in order of big O of n square, and so on. The next property is f of n is in big O of g of n if and only if g of n is in omega of f of n. If suppose f of n is in big O of g of n, what does it mean? F of n is less than or equal to some constant into g of n. Okay, so in that case, obviously, what about g of n? It will be greater than or equal to some constant into f of n. That is why if this is true, then g of n is in omega of f of n is also true. If the second condition is satisfied, automatically the first condition will also be satisfied. This is what is the second property. Then the third property is f of n is in big O of g of n. It means that f of n is less than or equal to some constant into g of n. Whereas this g of n, second function g of n is greater than, it is in big O of h of n. It means that g of n is less than or equal to h of n function. Okay, so here it means that f of n will be less than or equal to h of n. It implies that f of n is in big O of h of n. This is what is the transitivity property. Then the next property is if f of n is in big O of g1 of n and f2 of n is in big O of g2 of n, then f1 of n plus f2 of n will be equal to big O of maximum of g1 of n and g2 of n. Actually, this property implies that if the algorithm comprises two consecutive executed parts, then its overall efficiency is determined by the part with the larger order of growth, that is its least efficient part. The next property is based on order of growth using limits. If suppose t of n by g of n, limit n tends to infinity, t of n by g of n is equal to 0, when this will be equal to 0? If suppose order of growth of the numerator. What is the numerator? T of n. If order of growth of t of n is less than order of growth of the denominator g of n, then only this value will be equal to 0. If that is the case, it means that t of n is in big O of g of n. Then the second condition is if suppose limit n tends to infinity, t of n by g of n is equal to a constant which is greater than 0. When this will be a constant, if suppose order of growth of both the functions are same only, we will be getting constant value here. So the second condition implies that theta notation. Then the third value is if suppose the result, if limit n tends to infinity, t of n by g of n is equal to infinity. In that case, what does it mean? The numerator is a large value than the denominator. That means what? The order of growth of t of n is greater than order of growth of g of n. Then what's the relationship between these two functions, t of n and g of n? T of n is in big omega of g of n. Okay, so that is what is the condition here. And actually, based on this one, based on the definition of asymptotic notations, the first two classes means that t of n is in big O of g of n. Last two cases means that t of n is in big omega of g of n. And the second case means that t of n is in theta of g of n. Let's see some examples. 10n versus n square, which is satisfied. 10n is in big O of n square. Why? Because n is having lesser order of growth than the n square. Then the next one is n into n plus 1 divided by 2. So it can be approximately equal to n square. So n square versus n square, both the functions are having same order of growth. It means that theta notation. So n into n plus 1 divided by 2 is in theta of n square. So in this way, we can find the order of growth. Thank you, students.